Methods determining mechanism. As we know that in any chemical reaction, there must be a mechanism for that reaction. So what are those methods through which we can determine what kind of mechanism this particular chemical reaction have followed? So there are some methods we have. So first of all, analyzing the product form. By analyzing the product form, we can determine the mechanism of that reaction. Suppose we have an alkene or CH2 or CH double bond CH2, and when this alkene is reacted with HBr, we have two possibilities in this case. What are those possibilities? In the presence of peroxide and in the absence of peroxide. So in this particular reaction, we have two outcomes. In the presence of peroxide, this reaction will be CH2Br, and in the absence of peroxide, we will get okay. Thus we can see that there are two different outcomes for this particular reaction, and if we analyze this product, we can get to know that what kind of mechanism was followed up by this particular reaction. In second method, we have product stability and kinetic and thermodynamic control. In a chemical reaction, the initial products formed are kinetic controlled, and if we further delay that reaction to happen, then the reaction will be controlled thermodynamically. I'll explain how. Suppose we have a cyclohexanone, and we have a furan with an aldehyde group, and this is in the presence of semicarbazide. Okay. So, in case you don't know the structure of semicarbazide, it is this NH2, CO, NH, NH2. So what will be the products for this particular reaction? So in few minutes and within few hours. So in this reaction, within few minutes, the reaction product will be and this is called cyclohexanone semicarbazone. So in few minutes, cyclohexanone semicarbazone will be formed. But if we let this reaction for a few hours, we will get a different product, and that product will be and this can be named as phosphorus semicarbazone. This is cyclohexanone semicarbazone, and this is phosphorus semicarbazone. This product, which is found here, it is kinetically controlled, and second product, which is found here, this is thermodynamically controlled because of the time period that we allowed for this reaction to happen. In few minutes, kinetically controlled, and in few hours, thermodynamically controlled. So this is the difference by which we can tell the reaction mechanism for such reactions. Third method for determining mechanism is stereochemical consideration in product form. So in the most of the chemical reactions that involve stereochemistry are kinetically controlled. So, with knowing the stereochemistry of the product form, we can determine the mechanism involved in that particular reaction. Our next method for determining mechanism is study of intermediates. So in product, we can find whether there is an intermediate formed or not. Because if there is an intermediate, we can guess the mechanism of the reaction. Intermediates can be many. It can be carbocation, carbanion, it can be free radical, and it can be carbene. So these are our next method is separation of intermediates. So how can these intermediates can be separated in a reaction? So it can be separated in the initial time of the chemical reaction and in mild conditions. So we have to do hurry in separating the intermediates by keeping the mild conditions. For example, in this particular reaction, the intermediate can be separated as acetylene. So this is the intermediate in this particular reaction separated as acetylene. So in this way, by separating the intermediate and studying that intermediate, we can determine the mechanism of this reaction. But separating and intermediates involve two more steps. First one is trapping the intermediate, and then second is determining the intermediate. So for trapping, for example, we have benzene as intermediate, and so how will we trap it? We can use diene and react benzene to diene, and we'll see if there is any Diels-Alder adduct formed, and if there is Diels-Alder adduct formed, there will be benzene as intermediate. And after trapping the intermediate, we can use various techniques such as IR, NMR, and further spectroscopic techniques that are used for the determining for the intermediate. By studying catalysts, we can know the details about the reaction mechanism, because you can see that catalysts provide an alternative path to that particular reaction. So our next method is isotope labeling. So what does it mean, isotope labeling? It means that in most of the reactions in organic chemistry, different isotopes may react to give different products. So by knowing which isotope is in the product, we can determine the mechanism of that reaction. So isotope labeling is an important tool to know the mechanism of the reaction. For example, we have RCOO plus. So here we are using C14. Here we are using C14, which is radioactive, and it will give us BRCN. RCN. So we are using here 14C and reacting it with BRCN, and if the product is radioactive, then we conclude that the C here is also radioactive, that is C14. So you see that by knowing that the product is radioactive, we can assume that C here is C14, not this C. So this is the benefit of isotope labeling. I can give you one more. So what will be the product of this reaction? So by knowing the exact product of this reaction in terms of isotopes, we have to use H2 oxygen. It means the 18O isotope of oxygen is being used to react with this reactant. So there are two possibilities for this for the products. One is but the question arises, which bond of this oxygen or this oxygen is broken up in this particular reaction? If the acyl oxygen is broken or the alkyl oxygen bond is broken, which of these bonds are broken? So for determining it, we used 18O isotope of oxygen, and if this bond is broken, then it must be 18O must be in this acid, and if this bond is broken, alkyl bond, then the 18O isotope of oxygen will be used in this product. Okay, so you know the difference. What I want to convey here is that the question was whether this bond is broken in this particular reaction or OR bond is broken in this particular reaction. So we used 18O isotope of oxygen in this reaction, and there will be two products, and if this acyl bond is broken in this reaction, then the product will be, then the 18O isotope of oxygen will go here, and if this alkyl bond is broken of this reactant, then 18O isotope will be going to this product. So this is the benefit of isotope labeling. Last method is crossover experiment. So the question here is whether the reorganization of carbon skeleton is intramolecular or intermolecular. So we'll see with an example. We have this molecule, and another one is so we have these two molecules, and in this reaction, if we get two products, which means this rearrangement of carbon skeleton is intramolecular, and if we get four molecules in products, we will be showing that in results we have four molecules in reorganization of these molecules. But in this particular example, we will get only two molecules due to intramolecular reorganization. So how it will be? So this molecule will be in this reaction. This molecule will be turned out to be and similarly in this molecule we will get So in this particular example, we showed that there is intramolecular rearrangement of carbon skeleton. So this proves that this particular chemical reaction is intramolecular reorganization. So from this experiment also we can determine the mechanism, whether it is intramolecular or intramolecular. So these were all the methods. Thank you.